Okay, now we're going to work into a domain of hypothesis testing in which the parameters of the population are unknown. So far, just for examples really, we've been studying situations of hypothesis testing in which we knew some of the population parameters, like the population variance or its mean. In most situations of research, you don't know these things, and you have to estimate these things from samples. Now, the ability to do this, or the techniques to do this, were a great advancement in statistics because up until this time, no one knew how to handle this situation. It essentially was impossible to calculate the probability accurately if you didn't know what the population parameters were. The procedure called the t-test was invented by a man named Gossett, who was working for the Guinness Brewery, and he had a special problem on his hands of trying to figure out if the batches of beer were being made differently. So they'd make a batch of beer and it would have a different alcohol or sugar level than another batch. But of course, batches of beer are going to differ somewhat in those levels, no matter what, just by chance. You're not going to have exactly the same alcohol and sugar levels and other ingredients of beer to be constant every time. And he needed to figure out if the differences he was seeing was due to some systematic difference in how they were making beer versus chance. If it was chance, then they could keep doing what they were doing. If there was some systematic change in how the beer was being made, they needed to know that. Otherwise, the quality of the beer would change from batch to batch and fluctuate too much. And in general, in manufacturing, you want to keep variance small. You want to keep the consistency of your product the same so that when you develop a market and so on, everybody knows what to expect. One of the odd things about Gossett's contribution is that once he invented the t-test, he couldn't publish under his own name. Guinness wouldn't let him do that. So he published under a pseudonym, Student. And so the test is referred to as Student's t-test. Now the hallmark of a t-test is the calculation or the estimation of population parameters from the statistics of samples. And there has to be an adjustment to the probability judgments to reflect this. There's a systematic bias that comes in when you use samples instead of population parameters. And so you have to control for this bias, and you have to generate a t-distribution instead of a z-distribution, which I'll get to in another slide. The first thing we're going to go through is the t-test for a single sample. We're just going to go step by step, just like your textbook, from one sample for one example to the next, very methodically, through every combination or every permutation of the test. And you can see how it builds over time as we go through each part. T-test for a single sample. Now we're going to do an actual sort of example, a study here, to illustrate the t-test for a single sample. And that's where you have a single sample that you've collected, and you have a known population parameter of the mean, but unknown variance. Now usually you would know both the mean and the variance, but in this case, just to illustrate the example, we have a population in which we know the mean, but don't know the variability. So here's an example. Do students in my fraternity study more hours than the national average of 2.5 hours per day? Well, the 2.5 hours per day is the population parameter of the mean. And we don't know what the variability is. It could be that's the average of 2.5 hours, but some people might study, half an hour per day, and some people might study 10 hours per day. So we don't know how spread out the scores are in the population. We just know that the average is 2.5. And I want to do a study in which I have that piece of information. So I go out and conduct a survey of 16 men in my fraternity, and I discover that they study an average of 3.2 hours per day. Now I got to figure out if that 3.2 is significantly greater than 2.5. Now, as you might imagine, if you just went out and collected data on this, you would discover some numbers that are greater than 2.5. Suppose I did my survey and found that on average my 16 men studied 3 hours per day, or 2.7 hours per day. Well, that could have occurred by chance. Just me going out and collect 16 people. The odds, are that I'll collect some samples of 16 men who study more than the national average, but that could have occurred by chance, just by a factor of how I collected them, how I sampled them. So I need to go out, do a statistical test, and then figure out if the 3.2 was unlikely to have occurred by chance. And if it didn't occur by chance, then I reject the null hypothesis. I accept that 3.2 then is significantly greater than 2.5. Men in my fraternity are studying significantly more than the national average. So I have to go out and figure that out, and we'll do that complete test in the example here. Once again, we will go through the steps of hypothesis testing in order to test if the numbers are significantly different. Okay, step 1, as always, is to restate the research question as a research hypothesis and a null hypothesis, and refer to populations. Okay, so population 1 are students who live in fraternities, and population 2 are students who live in the general college population. And the research hypothesis will be the mean study time of population 1, students who live in fraternities, will be higher than the mean study time of population 2, students who live in the general college population. The null hypothesis will be the mean study time of population 1 will be the same as the mean study time of population 2. Step 2, determine the comparison distribution. Okay, well, the mean of population 2, all students living in the general college population, of 2.5, is the mean of the comparison distribution. As you remember, your comparison distributions and your population distributions will have the same mean. However, the variance of population 2, the population parameter there, is unknown. We don't know what the variability is. We just know that the average is 2.5. Now you can tell this is kind of a contrived situation. Usually if you know the mean of a population, you'll also know its variability. But in this case, just for an example, we don't know the variance. Now we're going to estimate the population variance from the sample variance. Since the variance of a sample will always be slightly smaller than the variance of a population, the estimate we make based on a sample is biased. It'll always be slightly smaller. So what we've got to do is calculate an unbiased estimate by using a slightly different formula for calculating the variance. And we'll explain that in the next slide. Okay, this is a continuation of step 2, determining the comparison distribution, and we're going to figure out a way to determine an estimate of the comparison distribution variance. You can get an unbiased estimate of a population variance by using a slightly different formula for calculating the variance. Ordinarily, the variance is equal to these differences of the scores to the mean. So you take the difference of the score, which is indicated here by x, minus the mean, and you square these differences, and you divide by n, which is the sample size or the population size. Well, an unbiased variance estimate is equal to the same sum of squares divided by n minus 1. The division of n minus 1 makes the variance estimate slightly larger. Now remember, when you're estimating from samples, the estimate is slightly smaller. So if you divide by n minus 1, you increase the variance estimate slightly, making it more consistent with the population variance. So you make an unbiased estimate of the population variance when you do that. Well, this number n minus 1 is got a special name. It's referred to as the degrees of freedom, or DF. It's the number of scores in a sample that are free to vary. And what that means is that, imagine if you know you have a sample of 10, you have 10 scores. Well, if you know the mean, or if you know the total number, the sum of those scores, only 9 of them are really free to vary. Because once you get to the ninth, once you know the ninth score, and you know the total of adding up all the sum of all these scores, then the 10th one can't vary. You'll know what it is and it can't vary. So in order for the 10 to add up to some sum, 9 can vary, 1 has to be determined. And so if you know the mean of a sample, or if you know the total of a sample of scores, then n minus 1 are free to vary, so that's the degrees of freedom. So the unbiased variance estimate is equal to the sum of squares divided by the degrees of freedom, and not by n. Okay, now we're going to calculate all these for our study hours example. Now remember, this is all leading up to calculating the population variance from an estimate from the sample. So now we have that estimate. We take the sample sum of squares, and we calculate that from the sample, and that turns out to be 9.6. Now remember, the sum of squares is the distances of the scores to the means, all squared and then added up, and here we get 9.6. Our degrees of freedom, which is the sample size minus 1, that's 16 minus 1, that equals 15. And now we can make our population variance estimate. The population variance estimate is equal to the sample sum of squares divided by the degrees of freedom divided by 15, which we calculate here to be equal to 0.64. Okay, that's that variance we were looking for we didn't have. So we had the population mean, and now we have an estimate of the population variance derived from a sample from the population. Okay, the next thing we need to do is calculate the standard deviation of the distribution of means. Now this is something we did before. So once you have the population variance, then you calculate the variability of the distribution of mean. Now remember from the interactive example, the interactive program, there was a distribution at the top that was blue, and we took samples from it and calculated the means of those samples and plotted those down below. We got a distribution down there that was much narrower than the one up top. And so we're going to get a standard deviation or a variance estimate of the distribution of means that's going to be narrower than the population variance. It's going to be smaller than the population variance. And it's smaller by the factor of the sample size. So if we take the variance of the means, it equals the population variance. In this case, we've estimated it up top there at 0.64, divided by the sample size, which was 16, and we get 0.04. Okay, that's the variance of the means. Now to get the standard deviation of the distribution of means, we have to take the square root of that number. So we take the square root of 0.04 and we get 0.2. That's the standard deviation of the distribution of means based upon the sample size of 16 and a population variance of 0.64. So now we're set up to start doing our hypothesis testing, now that we have the comparison distribution mapped out in the population variance estimate derived from the sample. Okay, we're still in step 2, determine the comparison distribution. The reason we're still in step 2 is because that's probably this is the area of hypothesis testing that's had the biggest impact from the t-test. And the distribution is not a z-distribution. It's not a perfectly monotonically decreasing bell-shaped curve like we saw with the z-distribution. The t-distribution is slightly different. It has to adjust for the error that results from estimating parameters from samples. So when you use an estimate of the population variance that's derived from a sample, there's more error in this, just in the judgment and the distribution and everything. So the distribution has to accommodate this by adjusting its shape, which is adjusting the probabilities and making them a little more conservative. This results in more extreme values in the distribution of means, so it's more spread out, and it's related to the sample size. So the distortion you see there, you see in this graphic of the normal curve, is a solid line. And you can see where it's monotonically decreasing as you go out toward the tails. The t-distribution has some little humps in it. See how the probability is different slightly at the tails of the distribution. As sample size increases, those humps diminish and become more normal looking. Because again, see, a larger sample is going to estimate the variance of the population better. There's going to be less error in making the judgment, and so the t-distribution will come to look like the z-distribution if the sample size is large. But these adjustments to the distribution are accommodations to the error that's caused by different estimating from samples. And it's more distorted the smaller the sample is. Okay, back to the shape of the t-distribution versus the z-distribution. The result of this is that the difference in the shape of the t-distribution affects how extreme a score must be in order for you to reject the null hypothesis. You need a slightly more extreme mean difference to reject the null with a t-distribution than with a normal distribution. Again, this comes from the error that's induced by sampling, estimating population parameters without knowing them directly. You can see where the probability is, doesn't attenuate quite as quickly in a t-distribution as it does in a z. And so it takes a little more extreme score to reach that alpha level of 0.05 than it does with a z-distribution. Again, this varies with the sample size. If the sample size is large, then the distribution looks very similar to a z-distribution. If the sample size is small, then you see more of that distortion in the tails that makes it harder to reject the null hypothesis. Here's a nice display showing the relationship between the sample size and the way in which the t-distribution is distorted. If you have a 0.05 alpha, which means you have a 5% cutoff for your chance level to reject the null hypothesis, if you have a z-distribution in which you know the population parameters, then the cutoff for 95% level is a z-score of 1.64. If you have a t-distribution and you have an alpha level of 0.05 and 7 degrees of freedom, which means your sample size is 8, because remember, degrees of freedom is 1 minus the sample size. So you have a sample size of 8, then your 95% cutoff for the t-distribution is a t-score of 1.89. So it's much larger than the 1.64. If you have a sample size of 25, in the next row down, you're going to be much closer to 1.64. That ends up having a t-score of 1.71. If you have an infinite sample size, if it goes all the way up to an infinite size, that means you're representing the population perfectly, and your degrees of freedom is the same as the population, and that results in a t-score of 1.64, which is exactly the same as the z-score for the 95% confidence interval. So if you take the t-distribution and calculate it out for an infinite sample size of infinite magnitude, then essentially you have the population. And so if you have the population, you've got the same cutoff as you would, as if you knew the population parameters. Now obviously this is just done for comparison. It's done to illustrate how much error is introduced by estimating from small samples. And you can see that there's a relationship clearly between the sample size and the cutoffs you need to reject the null hypothesis. Well, theoretically, there's a different t-distribution for every degrees of freedom. You'd have a slightly different shape to this curve for every degrees of freedom that you have. So every sample size would be represented slightly differently. Now, when you actually calculate t and you go and evaluate its probability, the tables usually only include cutoff points for common alpha levels, like 0.05 and 0.01, and then they'll have a demarcation for degrees of freedom that are reasonable. And so it'll go, degrees of freedom of, 3 or 5 up to degrees of freedom, essentially infinity. Because once you reach a certain level for degrees of freedom, like, sample size of 300 or 400, you essentially match the population. So the t-values don't change very much when you have sample sizes of, 301 or sample sizes of 403. That doesn't change much. The t-distribution doesn't change much over a sample size of, say, 300. So the tables will just have cutoffs for alpha levels. Now, SPSS will do something differently. SPSS will generate a probability for a certain t. It won't have a cutoff system because the calculations in SPSS are true calculations of t. They aren't constrained by having to make a table out of them. And so when you give the characteristics of your sample and so on to SPSS to analyze, it'll actually generate a probability associated with the t-value that it calculates. Then you can decide whether that probability level is a common needs for 0.05 or 0.01 or something else. And so it'll report a probability value of, say, something like 0.037. And since that's less than 0.05, people reject the null hypothesis and support the research hypothesis and so on. But you can see where it's given you the actual probability. It just hasn't told you, well, you met a cutoff or not, like a table would. You see, a table can't produce every t-value and every probability level that would be associated with every individual sample size. It would just make the tables. You could fill up a whole book with just tables if you did that. Here's an example of a t-score table, or part of one. You can imagine these tables going on for pages and pages. Here you have a separation of one-tailed tests and two-tailed tests. Now remember, the tail, this refers to whether you have a directional hypothesis or not. If I hypothesize that fraternity brothers should study more than other students, then I have a directional hypothesis, and I would use a one-tailed test. If I don't have any direction to my hypothesis, then I use two-tailed tests. At any rate, let's stick with the one-tailed test now just for the example. If I want to look up a cutoff score in my table, I choose my p-value, which you can see under the one-tailed test label there. P-values of 0.1, 0.05, and 0.01. And then on the far left, you see a column of degrees of freedom. So if I have 16 subjects in my sample, that means I have 15 degrees of freedom, and you can see there's a blue line there. And it's cutting across the different alpha levels for the one-tailed test. And I've chosen a 0.05 alpha level, which is the middle column. And as I go down this table, it's going to tell me what the cutoff t-score is that I need to reject the null hypothesis, given my 0.05 p-value and my degrees of freedom of 15. And I read that value in there as 1.753. So when I actually calculate my t-score, I want to compare it to this value to see if I can reject the null hypothesis. And we'll get to that in a later slide. But as you can see in these tables, it has just the demarcations for cutoff values. It doesn't have every t under every condition. All right, now we're going to calculate a t-score. It's very similar to calculating a z-score. They both involve comparing two means. In this case, the sample mean versus a population mean. So here's the formula for calculating a t-score. It equals the sample mean minus the population mean divided by the standard deviation of the distribution of means. Remember, we derive that standard deviation from an estimate of variance in the sample. Remember the whole process we went through of trying to figure out what the standard deviation of the distribution of means was. You can go back to that slide and look at it if you care to see how we got those numbers. Now we're going to calculate the t-score. We take the sample mean, which is 3.2, and we take the population mean, which is 2.5, and we subtract those. Then we divide by 0.2, which is the standard deviation of the distribution of means, and we get a t-score of 3.5. Which strikes me as a pretty reasonably large t-score. It suggests that relative to the variability in the sample and the population, the mean difference is quite large. But now we're going to go look this up in a table to find out if this t-score is going to beat chance or not. Well, here we are back at the t-table, and we've got to look up the t-score that's consistent with our cutoff. We've chosen the 0.05 level of significance, and we have degrees of freedom of 15. Again, that's 16 minus 1. If you go over by underneath the 0.05 levels and go down to where it has degrees of freedom of 15, you see that 1.753 there. So that's our cutoff value for t. If we get a t-score that's that level or higher, then it's unlikely that a t-score occurred by chance. It's such an unusual t-score, it's so extreme, that it probably did not occur by chance. And now we're going to compare our t-score of 3.26 to that score, and obviously our t is much larger, which indicates that our result, our mean difference, likely did not occur by chance. It's a very rare, sort of unusual circumstance that would have occurred by chance. So we're going to say, well, that's so rare, we're going to reject the null hypothesis that the means are the same, and we're going to support the research hypothesis that they're different, and that fraternity brothers, therefore, study longer hours than the average population. Here you see the situation depicted graphically. So up there we have the population distribution with its mean of 2.5. Now we've estimated the variance from the sample down below there, but the population distribution, looks like that. Now the comparison distribution, the t-distribution, is going to be narrower. Remember, now a distribution of means is going to be more constrained in its variance than the population it comes from. So that's going to be narrower, but the mean is the same. So they both have a mean of 2.5. Now we have our sample down there, 16 subjects that we surveyed. And there we got a mean of among those 16 people of 3.2 hours of study. And when we plot all this on the same number scale, you can clearly see that mean of 3.2 is way outside the range, the shaded area there, for a significant level of 0.05. So our t-score of 3.2 is very far from that mean of 2.5. You clearly see there's very little overlap, and the 3.2 is obviously statistically significant and probably didn't occur by chance. So we reject the null hypothesis, we support the research hypothesis, And we conclude that fraternity brothers spend more hours studying than students in the general population of students. All right, now we're going to learn about another kind of t-test. Referred to here as the t-test for dependent means, and it's used when you want to measure a dependent variable twice from each unit of observation. So you have two measurements from each person or each subject. Now they're referred to as dependent means because they're dependent on each other, they're correlated. And what you're going to do is basically take the two measurements and subtract them and get a different score, which ends up being a t-test for a single sample again. But it's this twist in which you've got two observations on the same subject. And these are very common. This is a common model to study changes associated with interventions, like learning interventions or drug trials. They often use dependent measures t-tests. And here we have examples. So you take scores on a reading test before and after phonics training. So you give a class phonics training. You measure their reading ability before they take the training and then afterwards, and what you end up with is two measurements on the same people that you want to contrast. Another one is rating on the safety of flying versus the safety of taking a train when it's collected from the same people. So you have them make judgments about safety. Ratings on the taste of Pepsi versus Coke when collected from the same people. The ratings from the same people on two different types of drink, but since it's ratings from the same people, those ratings are going to be correlated. And what you're interested in is the contrast between Pepsi and Coke among the same people. And then finally we have an example here, the speed of someone driving in a car before and after seeing a police checkpoint for speed. And we all know that affects people's behavior. And so before and after should show a contrast. So what we're going to have is a t-test set up to show the contrast between two states or two ratings, two measurements taken on the same subjects.